So in this video we are still on the chapter of divisibility in integral domains, and in this video we show that the ring of polynomials with integer coefficients is not a principal ideal domain. Okay, we are going to consider this. I use the word I for ideal. Okay, so we are going to consider this ideal, an ideal in this form: ax plus 2b such that a and b are in the integers. So in order for this ideal is in the ring of polynomials, right? So if the ring of polynomials is a principal ideal domain, there should be a generator, right? Remember that every ideal is generated by a generator. Okay? Okay. So since we have an ideal here, of course a polynomial 1, this ideal should be generated by some polynomial. I'm going to call it h of x. Okay? Since this ideal is in the ring of polynomials under integer coefficients. So to give you an idea of what kind of polynomials you are getting in this ideal here, I made a list of some particular polynomials you will get here. So for instance, if a is 0 and b is 1, then you have f1 of x, it will be 2. Now if b is 2, another polynomial, it will be 4. Another polynomial can be minus 4, since this is a and b are in the integers. If b is 0 then and a is 1, you'll get a polynomial like this one, x or 2x or minus 3x or 3x, etc. And if this a is 1 and b is 1, you might have x plus 2 or x plus 4 or 2x plus 2. So this is the kind of polynomials you're going to get in this ideal. Okay, but we suppose that it is an ideal, and we suppose that it is generated by a certain polynomial. So for instance, this polynomial 2 should be generated by h of x, right? So we should have h of x times some f of x, and we would get, for instance, 2. And the same, for instance, this one here, x, we should get h of x, the generator, times, well, we have to some other polynomial. Okay, so this should happen if this was if this ideal was generated by a certain h of x. This should happen. But look at this polynomial. This is degree 0, right? So the degree of constant polynomial 2 is 0. Okay. So due to the degree rule, the degree of this polynomial, adding these two polynomials, so the degree of h of x, this one, plus the degree of f of x, this should be 0. Okay, but this cannot happen unless they are both 0, right? Okay, so if the degree of h of x has to be 0, h of x must be a constant polynomial, right? Okay, but the generator times a polynomial, we should get 2. So h of x can only be something like plus or minus 1, right? For instance, if h of x is 1 and f of x is 2, 2 times 1 we would get 2. Or if h of x is minus 1 and f of x is minus 2, then we would get 2. Okay, so here it's okay. But h of x could also be, or it could be plus or minus 2, right? If h of x is 2, f of x is 1, 1 times 2, we get 2. That would be okay. Well, this one, we can take it off, because here in the ideal there is no 1 here. We have 2 and we have minus 2, but we don't have 1, so this one is out of question. So we only have h of x can only be plus or minus 2. But this being said, for this it is okay, but here we have a problem, because how are we going to have x equals plus or minus 2 times g of x? You see, you're getting rational coefficients. They should be all integers. You see, this doesn't make sense. Okay, so it is proved that since this ideal is in this ring of polynomial with integer coefficients, since this ideal is here, we proved that, for instance, this ideal has no generator, right? And since this ideal has no generator, you see, this ring of polynomials is not a principal ideal domain.